Okay, so now we're at a point where we got to think about reality a bit. And it has to do with the fact the resistance of the inductor coil cannot be ignored. It's got a real value to it. So if you try to hook up a capacitor and an inductor in parallel like this, you're going to have this sitting around. It's parasitic, no matter what you do. So here's the admittance, and we make the numerator real by this procedure right here, multiplying by the complex conjugate of the denominator. And so with a little rearrangement, you have this formula for the admittance. You want to make, at resonance, this stuff's going to equal 0. Okay, so you find out what it is, and you solve for omega. So omega at resonance is given by this formula here. It's pretty easy to invert this equation. And omega naught is still defined this way, Q naught this way, so we can get some. Omega R is not going to equal omega naught. That's the point. That's part of the point right here. There's the formula expressing the two. At resonance, the voltage and impedance are at the maximum. Z max, let's see, Z is 1 over Y. Here's Y right here. So we can invert this equation. And it gets hairy. We can just take the reciprocal of Y. Hairy a bit. Let's see, is it really that bad? No, it's not really that bad. There we go. Because we're just looking at what it is at resonance. This is going to be 0 at resonance. So we find Z, we rearrange it a bit and express it in terms of omega R. Okay. So here we have Z max is R Q naught squared. Now, here's Q naught way down here. And is this the quality factor? That's kind of the question. Is that the quality factor? How do you define a quality factor for a circuit like this? It's usually the dissipative term. It's a quality factor that's going to be a function of the frequency, and which doesn't make sense. Maybe you can just look at how much, when you look at the response of the circuit and you have a bandwidth, the half power bandwidth, is this a good definition? Maybe so. It's not bad. It's pretty close. Okay, moving on. So we have this circuit, which we just developed the formulas for this in this slide. You guys go ahead and do this one. I'm going to leave that as an assignment for you. I'll just finish this up. It asks you for two different resistors, the values of two different resistors. What's going to happen? How is the resonance going to change? And we see, and here's a table that expresses that. And you can check bandwidth is omega over the quality, just on these two, to get the idea that, yeah, it's not too bad. The same ideas still apply. That you're going to get a resonance for a good quality, you're going to have a high peak. For a poor quality, you're going to have a low peak. A high quality, by the way, you'll notice when this factor goes up, these two get closer to each other. This usually means, keeping the resistance low usually means fatter wires. It also usually means, fatter wires, and which actually reduces the inductance, the big fat wires. We can use ferrite cores, magnetic materials in the cores of these things, to raise the inductance. Okay, taking a general look, here is, for a series circuit, here's the equation, the admittance for a parallel circuit, and impedance is a minimum at resonance. For the series, the impedance reaches a maximum, or the admittance reaches a minimum for a parallel. So we write down the equations. These quadratic terms, this is the damping factor, this is zeta. And we can use, we can redefine our equations in terms of this zeta. There's a reason we want to do that. That this 2 zeta is 1 over the quality. And in both cases, series or parallel. So we can just use, we can look at the quadratic equation in general. We can re-express it in a form that looks like this. If we can re-express our impedances or admittances so it looks like this kind of equation, then we've got our quality, the Q of the circuit. And this is L over R, by the way. Conduct G is equal to 1 over R. Okay. Scaling. Why might you want to do that? So I'm going to go through this stuff kind of fast. We scale circuits a lot. We scale things a lot. We want to know on a large scale, how will something behave? We can make a model at a small scale. So we can model something big with something small. So we can just change all the magnitudes, but we won't change the resonance frequency or the quality. Just scale L, R, and C. You can do time scaling too. And the reason you might want to do that, here's how you have to do if you scale for time. The reason you might want to do that is you want to model a system maybe that changes slowly, but you want answers fast. You want to model. We build electrical circuits to model real systems like the Mississippi River or some river system or something. And there's rains going on. We have this electrical circuit laid out, and we turn a dial that says, well, the rain in the next hour is, or the next day is going to be 12 inches of rain. We expect 12 inches of rain. So let's turn this dial on this circuit and ask, will it flood? And it says, yeah, it'll flood. Well, what happens if we open the floodgates on this dam? You let all the water through. The water rises instantly, and you say, how much do we need to let in so that it doesn't overflow the banks? And so you drain the reservoir, and then the rain comes down and fills up the reservoir rather than flooding the river. This is why you do that. So in a few minutes, you can get an answer to a problem that's going to take 24 hours, and you can play what-if games. Okay. You can keep the Q constant. Scale the frequency. Okay. So let me go through this example. I will go through this example, but I'm not going to go through it until the next video.